In this video, we're going to look at the index laws. These are the laws that we use when it comes to simplifying expressions that have powers in them. For those who don't know me, my name is Chris Ionazoni. I used to work as an engineer for a defense company, and I've since left that to start a career in tutoring. I make these videos so that VC students can do the best they can in math methods. With that out of the way, let's get into it. Before we dive into the specifics, it's worth understanding the terminology. A term of this form is either referred to as a power function or an exponential. The power is the letter or number at the top of the term. This might be referred to by other names such as the index or the exponent. The base is the term that is being raised to a power, which in this case is labelled as b. If two terms with the same base are multiplied together, then their powers will add. You would already know this from polynomials. If I have x to the power of 5 multiplied by x squared, I now have x to the power of 7. The same is true even of fractional powers. In this case, we have x to the power of 3 over 2 multiplied by x to the power of half, which, when added together, just gives you x to the power of 4 over 2, or further simplifies to just x squared. The division law is the opposite. If you have two terms that are divided, which have the same base, then their powers subtract instead. If I have x to the power of 5 divided by x squared, I now have x to the power of 3. This could show up as a division symbol or as a fraction. As before, this also works with fractional powers as well. If I have x to the power of 3 over 2 divided by x to the power of a half, I now have x to the power of 2 over 2, or just x. If my term has powers that are stacked onto each other, then those powers can be condensed down through multiplication. If I have x to the power of 5 and then that term is raised to the power of 3, then I will now have x to the power of 15. As before, this also works with fractional powers. If I have x to the power of 3 over 2 and that is raised to the power of 3, then I now have x to the power of 9 over 2. The last of the index laws tells us how to distribute the power if the base is a product of two different terms. Under these circumstances, you may distribute the power to each of those terms in the product. For example, if I had 5 by 3 all raised to the power of 2, then I could instead have 5 squared multiplied by 3 squared. As with all the other laws, it works with fractional indices as well. 5 by 3 to the power of a half is the same thing as 5 to the half multiplied by 3 to the half. Nicely enough, this also works with division as well. If you have a division of two terms that are both raised to the same power, then that power can be distributed through both the numerator and denominator. Before we move on to some of the more complicated examples, it's worth understanding some of the identities of index laws. The first is that anything to the power of 0 is going to equal 1, unless your base is 0, in which case that would be considered undefined. The next is this idea of negative indices. If you have a negative index, that simply implies a fraction. If I have x to the power of negative 2, it's the same thing as saying 1 divided by x squared. So the rule is basically just to put the base on the denominator and then flip the sign to positive. If the base is already in the denominator, then you flip it to the numerator instead. Lastly, fractional indices can be rewritten as roots, where the denominator of that fraction is the order of the root, and the numerator of that fraction is the power. You can write these in any order that you like, but usually the second representation is the easiest. For example, it's much easier to square root 9 down to 3 and then cube that up to 27 than it is to cube 9 and then try to square root that down instead. From here, we'll start looking at some examples and then slowly raise the difficulty over time. In this example, we have a combination of the multiplication and division principles. Under these circumstances, I recommend evaluating the numerator and denominator individually using the multiplication principle first. The new power of the numerator now becomes the power of the first term plus the power of the second term. When we do that, we achieve 5x plus 2x plus 1, which simplifies down to just 7x plus 1. We do the exact same thing for the denominator. 3x plus x is going to give us 4x. Now that we've done that, we just use the division principle, which just means we're going to take the power of the numerator and subtract the power of the denominator. When we do that, we're going to get a final power of b to the 3x plus 1. In this case, we have a similar situation. The only difference here is that we have more than one base. All that means is that we look at each base separately. The overall strategy is going to remain the same. We're going to start with the multiplication principle on the numerator and denominator, and then finish up with the division principle. In this case, we have a squared and a to the power of 5, which are going to combine to give us a to the power of 7. We also have b and b squared, which when combined make b cubed. As for the denominator, there's nothing to actually do here, so we can move on to the division principle. Again, we're just going to go term by term here. we have a to the power of 7 on the top and a to the power of 2 on the bottom. When combined, this is going to give us a to the power of 5. We also have b cubed on the top and b to the power of 4 on the bottom. When you perform the subtraction, this is going to give you b to the power of negative 1, which is fine, but if you want, you can express this as a division instead. It's purely optional though. Now we're starting to look at some more complicated expressions. When you have cascaded powers like this, it's usually easiest to start by distributing those first. That means that every term in the first set of brackets is going to have its power multiplied by 3, and every term in the other bracket is going to have its power multiplied by 2. Once we've achieved that, we're just going to go back to the old strategy. If we look at the numerator and denominator of the first term, there is no more multiplication to be done here, so it's time to use a division law. There's a couple ways you could handle this. My preference is to keep everything in the same row, so I'll be using negative indexes, but feel free to leave it as a fraction if you prefer. And then to top it all off, we have yet another division principle, because we have two terms that are divided by each other. Just don't forget that when you perform the subtraction on a negative, that becomes a positive. In the final example, we're going to look at a strategy called prime decomposition. This has actually become one of my favourite ways of simplifying tougher fractions. So not only do we use this strategy for the index law style questions, but you can also use it if you have trouble with simplifying fractions. So if that's you, pay attention. Our main trouble in this circumstance is that the index laws only work if you have the same base, which works fine for the 5, but what about the 10 and the 8? They're kind of just hanging there. Prime decomposition means breaking down the bases into their prime factors. For example, 10 can be broken down into 5 by 2, and 8 can be broken down into 4 by 2, or even further, down to 2 by 2 by 2, which is the same thing as just 2 cubed. From here, we can split the 5 and the 2 in the numerator up into their own separate terms. And suddenly, we now have more index laws available to us. Starting with the cascaded powers, 2 to the power of 3 to the power of n is now going to become 2 to the power of 3n. Now we move on to our multiplication principle. The only thing to do here would be to combine the 5 to the 2n and the 5 to the n to make 5 to the 3n. And we're just going to finish up with division. 5 to the 3n and 5 to the n are going to make 5 to the 2n, and 2 to the n and 2 to the negative 3n are going to become 2 to the negative 2n. You can write this as a fraction if you want, but that's optional. In fact, if you do write it as a fraction, you might as well go the extra mile and also take out that common power out the front. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.